Hello everyone. Myself, Dr. M. Pavan Kumar Reddy, Assistant Professor, Department of Mathematics, VNR JYOTHI Institute of Engineering and Technology, Hyderabad. Today we learn complex matrices and its properties, which is part of the course Matrices and Calculus. The content in this: complex matrix, Hermitian matrix, square Hermitian matrix, unitary matrix, properties of complex matrices, and problems on complex matrices. Okay. First we learn what is complex matrix. So complex matrix means if at least one element of the matrix is a complex number. Complex number is, say, A plus IB is the complex number. This is where this A and B both are real numbers. A and B are both are real numbers. Here I is root over -1. Okay. So a matrix, at least one element of the matrix. See, this is the general matrix of order m by n. M rows and n columns. If at least one of the element in this matrix is a complex number of the form A plus IB, the matrix is said to be a complex matrix. Complex matrix. Let's see one example of a complex matrix. Observe here. See, A is a 2 by 2 matrix. The number of rows is 2 and number of columns are 2. See, the first element is 2 plus 3i. It is in the form A plus IB, where 2 and 3 are real numbers, and this is -7i. Of course, there is no real part, but it is a complex number. 5, which doesn't have imaginary part, even though we can say it is a complex number, since we can write 5 plus i0, and 1 minus i. So at least one element of the matrix is a complex number. The matrix is said to be a complex matrix. Okay. Now, let's see conjugate of a complex matrix. So conjugate of a complex matrix means, suppose if you have a complex number of the form A plus IB, the conjugate of a complex number is by changing the sign of the imaginary part. So the imaginary part is here B. Its sign is here, we have plus, replace it with minus, we get this is the complex conjugate of A plus IB. A minus IB is the complex conjugate of A plus IB. So a conjugate of a complex matrix means we have to replace every element of a complex matrix with the corresponding conjugate complex number, with the corresponding conjugate complex number. The so obtained matrix is called a conjugate matrix of A. Conjugate matrix of A. Generally, the conjugate matrix of A is denoted by A bar. A bar. Okay. See, let's see an example on conjugate of a complex matrix. That is, suppose if you take the matrix A as 2 plus 3i minus 7i 5 1 minus I. Now the conjugate of this matrix is denoted by A bar, which is we have to replace here every element with the respective conjugate element. 2 plus 3i, its conjugate is 2 minus 3i. Okay, minus 7i. So conjugate is, it doesn't have any real part, but its conjugate is, we have to change the sign of imaginary part, which is plus 7i. Okay. Now 5, it doesn't have any real part. It doesn't have any imaginary part. So therefore, the conjugate of this number is itself. Now 1 minus I, the conjugate is 1 plus I. Okay. So now this is the conjugate of the matrix A. Okay. Let's see. This is A bar. It is 2 minus 3i plus 7i 5 and 1 plus I is the conjugate of a complex matrix. That is, every element is replaced with the corresponding conjugate of the complex number. Okay. Next, it's a transposed conjugate of a matrix. Transposed conjugate of a complex matrix. So already we studied just now conjugate of a matrix. Now transposed conjugate of a matrix means, first we replace every element of the complex matrix with the respective conjugate element. Okay. And we interchange the rows and columns, we get the transposed conjugate of the matrix. The transposed conjugate of the matrix is generally denoted by this is A. This is transposed conjugate of A, which is nothing but we denote it as A theta. A theta is the So now let's see one example. See, this is the matrix we have. First we write the conjugate. The conjugate of the matrix is A bar is equals to, okay, it is, we replace every element with its conjugate. 2 plus 3i, conjugate is 2 minus 3i. Minus 7i, the conjugate is 7i. And 5, the conjugate, since it is a real number, its conjugate is itself. 1 minus I, the conjugate is 1 plus I. This is A bar, which is a conjugate of the matrix. Now we need transposed conjugate of the matrix. Transposed conjugate means we interchange rows and columns. So that is, first row can be written as first column, second row can be written as second column. That is, now it is A bar. We need transpose of this. Transpose. This is equals to, say, it is 2 minus 3i. First row I am writing as the first column. Interchanging the first row with the first. So now, and the second row as the second column, which is 5 and 1 plus I. 1 plus I. See, this is transposed conjugate. Also, this is denoted as simply A theta. A theta. Of course, some authors follow the notation A star also. Okay. But I am following this notation A theta. Okay. Throughout this topic, A theta. Okay. This is now. See, this is A theta equals to, see here, 2 minus 3i, 5, 7i, 1 plus I. This is the transposed conjugate of a complex matrix. Transposed conjugate of a complex matrix. The next one. See, now observe here, it is, we can see even first we are making it, first we are finding conjugate matrix, next we are transposing it. But suppose if you first find transpose, next you determine conjugate, also you get the same. That is, see, it is easy to see the conjugate of the transpose of A. So here, this is transposed conjugate of A. Conjugate transpose of A is denoted as A. This is transposed conjugate. Both are same. This is conjugate transpose of A, which is same as transposed conjugate of A. That means first we find transpose of the matrix, next we determine the conjugate. First we determine the conjugate, next we determine the transpose. Both are same. Both are same, which is denoted by A theta. Both A theta is nothing but we also called transposed conjugate of A or conjugate transpose of A. Both we can denote as A theta. Both we can denote as A theta. Okay. Next, Hermitian matrix. So a square matrix, let us take a square matrix is the generalized matrix A. A is equals to Aij, M by N, M rows and N columns. But here this is M rows and N column in general. But actually the Hermitian matrix must be a square matrix always. Here it is always it is N by N only. N by N. That is number of rows and columns must be same. Hermitian a matrix A, a square matrix A is said to be a Hermitian matrix if A theta equals to A. What is mean by A theta? Just now we studied. A theta means transposed conjugate of A. That is transposed conjugate of A is equals to A. That means if you have a matrix A, first you find conjugate of that, then find the transpose, which if you get the same matrix A only, such matrix A is said to be a Hermitian matrix. Such matrix A is said to be a Hermitian matrix. Let's see an example. See, this is the matrix A is given. It is a 3 by 3 matrix. 3 rows and 3 columns we have. Now, at least one element is a complex number. Yes, it is a complex number. So, this is a complex matrix. Okay. Now, first to verify whether it is a Hermitian matrix or not. First, we'll find conjugate of the matrix. That is A bar, which is, now it is 5 is a real number, so its conjugate is itself. 2 plus I, the conjugate is 2 minus I. Minus 3I, the conjugate is plus 3I. 2 minus I, the conjugate is 2 plus I. 1 minus 3, it is a real number, so its conjugate is itself. 1 minus I, it is 1 plus I. 3I, it is minus 3I. It is purely imaginary number. 1 plus I, it is 1 minus I. And 0 is a real number, its conjugate is itself. So this is A bar. Okay, that is conjugate of a matrix. This is a conjugate of a matrix. Now, transposed conjugate of the matrix we'll see. Transposed conjugate is A bar transpose. That is equals to. Now, we interchange rows and columns. First row as first column, that is 5. 2 minus I, it is minus 3I. Okay. Now it is second row as 2 minus I, 2 plus I, and minus 3 and 1 plus I. Now coming to third row as third column, it is minus 3I, 1 minus I, and 0. Observe carefully here the matrix A and the matrix transposed conjugate of A. Okay, see here, first row is 5, 2 plus I, minus 3I. Here also the same, 5, 2 plus I, minus 3I. Here the second row, 2 minus I, minus 3, 1 minus I. Here 2 minus I, minus 3, 1 minus I. Third row, 3I, 1 plus I, 0, and 3I, 1 plus I, 0. That is A. This is actually the matrix A itself. So from this we can say it is A theta equals to A, means the given matrix A is a Hermitian matrix. Okay, so this is. Now let's see one point. Here, observe here carefully in diagonal elements of the Hermitian matrix. All the diagonal elements of Hermitian matrix are real. All the diagonal elements of the Hermitian matrix are real. 5, minus 3 and 0. These are all real numbers only. They doesn't have any complex imaginary part. So from this what we can say is all the diagonal elements, principal diagonal elements of Hermitian matrix are real. Okay. And all other elements are the complex numbers. Okay. Next, we'll see what is skew Hermitian matrix. Here also a square matrix, of course it is generalized matrix. A square matrix is always it is n by n or m by m you can take. So a square matrix n by n is said to be skew Hermitian. If A theta equals to minus A. What is mean by A theta? We know. Transposed conjugate of A equals to negative of the given matrix A. Then such matrix is said to be a skew Hermitian matrix. Let's see an example. So the matrix is A. Let us take this one. So first we determine the conjugate of the matrix. It is A bar is equals to, see the conjugate of this, 3I conjugate is minus 3I, and 1 plus I conjugate is 1 minus I. 7 conjugate, since it is a real number, its conjugate is itself. Minus 1 plus I, so it is minus 1 minus I, and 0, and it is minus 2 plus I, and minus 7, it's a real number, it is itself. 2 minus I, it is conjugate is 2 plus I, minus I conjugate plus I. This is A bar. Now let's determine transposed conjugate of the matrix. Transposed conjugate, that is we interchange rows and columns. That is first row as first column, minus 3I, minus 1 minus I, and it is minus 7. Okay, minus 3I, minus 1 minus I, and minus 7. First column as first row. Second column as second row. That is 1 minus I, 0, and 2 plus I. third row as third column as third row. It is 7 minus 2 plus I and I. So this is. Now see, let's take minus common from this matrix. Let's take minus common. That means minus 3 I know. We are taking minus common means this becomes plus 3I. Here if you take minus common we get 1 plus I. Here if you take minus common we get 7. And here it is minus 1 plus I. This is 0. And it is minus 2 minus I. And it is 7 minus 7. And plus 2 minus I. It is minus I. Observe now carefully. This is minus 3I. The first row of the matrix A is 3I, 1 plus I, 7. The same as here. And second row is minus 1 plus I, 0, minus 2 minus I. Third row is minus 7, 2 minus I, minus I. Which is same as A. Same as the elements of A. So this is minus A, we can write simply. So the means we found that here A theta is equals to minus A. A theta equals to minus A. That is, we can say here the matrix A is skew Hermitian matrix. Matrix A is skew Hermitian matrix. If you observe carefully the principal diagonal elements of the matrix given, the principal diagonal elements of the matrix given are purely imaginary or 0. Purely imaginary or 0. That means the numbers, the elements along the diagonal doesn't have any real part. Either they are purely imaginary or 0 only. So that is a point. In a skew Hermitian matrix, the diagonal elements are either purely imaginary or 0. Okay. See this is. And the next one we'll see is a unitary matrix. Is a unitary matrix. Now a square matrix. Square matrix, of course, here it is again, it is n by n or m by m. Okay. A square matrix A is said to be a unitary matrix if A into A theta equals to A theta into A equals to I. That means the product of the given matrix and its transposed conjugate is equals to the product of the transposed conjugate of A and the matrix given, which is equals to the identity matrix of order A. Okay, identity matrix of order A. This is, if this holds, we can say the matrix A is a unitary matrix. Is a unitary matrix. Let's see an example of unitary matrix. See this is. So take an example of 2 by 2 matrix. Here 2 rows and 2 columns we have. A. Let's determine first A theta. That is, see, determine A bar. First we determine the conjugate of the matrix. The conjugate of the matrix is, the first one is, it is a real number. So we write as it is, its conjugate is itself. Second is also a real number, one first row, second column. And the conjugate of this one is minus I by root 2. And the conjugate of this is plus I by root 2. This is A bar. This is A bar. Now, transposed conjugate of A. Transposed conjugate of A is generally denoted by A theta. Also, we can write this as, it is transposed conjugate of A, which is, now, transpose, interchange rows and columns. It is first row as first column, that is 1 by root 2 and 1 by root 2. Second row as second column, it is minus I by root 2 and plus I by root 2. So, this is the transposed conjugate of A. Now let's consider the product, that is A and A theta. A into A theta. A into A theta, which is equals to, what is the matrix A? It is 1 by root 2, 1 by root 2, I by root 2 minus I by root 2. This is. Now, what is the matrix A theta? It is 1 by root 2 minus I by root 2. This is 1 by root 2 and I by root 2. Now multiplying these two matrices. Okay. So now first row, how to multiply the two matrices? In order to get, this is a 2 by 2 matrix, is also a 2 by 2 matrix. So now the resulting would be also a 2 by 2 matrix. So number of columns in the first matrix is equal to the number of rows in the second matrix. So the matrix multiplication is compatible, and the resulting matrix would be of order number of rows in the first matrix and number of columns in the second matrix, that is 2 by 2 again. Now how to get the first row first column element? That is by multiplying the corresponding elements of the first row of first matrix with the corresponding elements of the first column of the second matrix. That is 1 by root 2 into 1 by root 2. 1 by root 2 into 1 by root 2 is 1 by 2. Okay. Next, plus 1 by root 2 into 1 by root 2 is also 1 by 2. 1 by 2 plus 1 by 2. Next, first row second column element, that means multiply the first row elements with the second column of the second matrix. 1 by root 2 into I by root 2 minus I by root 2. Therefore, it is minus I by 2 minus I by 2. Root 2 into root 2 is 2. 1 by root 2 into I by root 2, which is plus I by 2. Plus I by 2. Similarly, the second row, first column element, that is I by root 2 into 1 by root 2, which is I by 2, minus I by root 2 into 1 by root 2, which is minus I by 2. Minus I by 2. Similarly, the second row, second column element, that is I by root 2 into minus I by root 2. Observe here, I by root 2 into minus I by root 2. Root 2 is 2. I into I, which is I square. I square is minus 1. Minus into this minus becomes plus. So therefore it is 1 by 2. It is 1 by 2. Similarly, minus I by root 2 into plus I by root 2. Minus I into I square. So minus 1. Minus into this minus becomes plus. So it is plus. And root 2 into root 2, which is 2. It is 1 by 2. Now, see, observe here carefully. This is minus through 1 minus I by 2 and plus I by 2 gets cancelled. Plus I by 2 and minus I by 2 gets cancelled. And 1 by 2 plus 1 by 2, which is 1. And this is 0, 0, and it is 1. Which is actually the identity matrix of order 2. Identity matrix of order 2. Simply we can write it as I2. I2. That is A into A theta. A into A theta is equals to 1001, which is I. So similarly we can prove A theta into A is also I. Okay, I am leaving it as an exercise. So A theta into A also I. This is. So therefore the matrix here given is 1 by root 2, 1 by root 2. I by root 2 minus I by root 2 is a unitary matrix. And here, if you find the determinant of this unitary matrix, we get either plus 1 or minus 1. If you find the determinant, let's see what is the determinant of this matrix. See, determinant of A. If you determine determinant, what is that? It is simple 2 by 2 matrix. If you consider this as A and this is B and this is C and this is D, if you consider the determinant of 2 by 2 matrix is AD minus BC. AD minus BC, which is, see, 1 by root 2 into minus I by root 2, which can be written as simply minus I by 2. Minus I by 2. Now, it is minus BC. B is 1 by root 2, C is I by root 2. So minus, it is I by 2. Minus I by 2. Okay. Minus I by 2, simply we can say it is minus I. Minus I. So this is determinant of the matrix. The absolute value of the determinant is, the absolute value of this one is absolute value of a complex number. Absolute value of a complex number, which is equals to, it is root over a square plus b square. That is root over square sum of the squares of the real and imaginary parts. In the similar manner, if you consider the absolute value of this minus I, which is equals to root over, there is no real part, it is 0, plus imaginary part is minus 1. Don't consider I. Imaginary part is the coefficient of I. Minus 1 whole square. That is root over 0 plus minus 1 whole square is 1. The answer is 1. That is, from this what we can say, the determinant of a unitary matrix is the absolute value of the determinant of the unitary matrix is 1. 1 or minus 1. Plus or minus 1. Okay. See, the determinant of a unitary matrix is of unit modulus. Unit modulus means either +1 or -1 we get as the determinant of absolute value of the unitary matrix. Okay. Now, next. So the properties of complex matrices. Properties of complex matrices. So what is the first one? It is conjugate of A. That is, you have a matrix A. First we determine the conjugate of the matrix. Again, if you determine the conjugate, we get the same matrix. We get the same matrix A. Similarly, second property, it is you have two matrices. Let us consider A and B. We add two matrices or we subtract two matrices. After adding or subtracting, you determine the conjugate of the matrix, which is same as, that means first we consider addition. That is, you have two matrices A and B. First we add them and then determine the conjugate of the matrix, which is same as first we find the conjugate of A, conjugate of B, and later we add. That means first we add the matrices, later we find the conjugate of the matrix is same as the addition of the two conjugate matrices. Addition of the two conjugate matrices. That is, first we determine conjugate of A and conjugate of B, later we add. Both are same. This property is also same for subtraction. Okay. The another property, this is, suppose you have a matrix A which is multiplied with some complex number, say 1 plus I into A, and then you determine the conjugate of this matrix. That is, A is the some complex matrix given and get it multiplied with some complex number, say 1 plus I. Now, if you find the conjugate of this matrix, which is same as simply the conjugate of the complex number into the conjugate of the matrix A. Conjugate of the matrix A. Here K is any complex number. K is any complex number. If K is any real number, then K complement is K itself, since a conjugate of any real number is itself. Okay. Now, similarly, this is now product of, say, A and B are two matrices. If you consider the product of the two matrices, later you find the conjugate of the matrix. Later you find the conjugate of the matrix, which is same as first we determine the conjugate of the respective matrices and then multiply. That is, conjugate of the product of two matrices is same as product of their conjugates. Product of their conjugates. And here the matrices A and B must be compatible for multiplication. The matrix A and B must be compatible for multiplication. So we see few more properties. This is, see, it is transposed conjugate of A is nothing but A itself. That is, this is looks similar like A bar whole bar is equals to A. That is the same. It is A theta whole theta. That is, first you find the transposed conjugate of A. Again, if you do the transposed conjugate of that, the matrix A only you get. Okay. And similarly, the same property like for conjugates, it is also applicable for transposed conjugate. That is, first you add two matrices or subtract two matrices. Later you determine the transposed conjugate of that, which is same as the addition or subtraction of their respective transposed conjugates. This is okay. Next, similarly, this is K into A theta is equals to K bar into A theta. Since here it is Ka theta, that is transposed conjugate of Ka. You have a matrix A, multiplying it with some complex number, say K. Then later you determine the transposed conjugate of that, which is same as transposed conjugate of A, get it multiplied with some conjugate of the complex number. So here no need to write K theta, since K may be a complex number, so its conjugate exists. But K is a number, it is a scalar. The transpose of scalar is itself. Since it is a 1 by 1 matrix, the conjugate of the matrix is itself. Okay, so that's why we write just only conjugate, not transpose. K conjugate into A theta, K being any complex number. Okay, and now the product of transposed conjugate of product of two matrices is equals to product of their transposed conjugate in reverse order. Product of their transposed conjugate in reverse order. That is A into B. First you are multiplying the two matrices. Later you are determining the transposed conjugate of that, which is same as the product of transposed conjugate of A and B in reverse order. That is B first, A next. So these are the properties of complex matrices. Now the properties of complex matrices for eigenvalues we have. That is, see, already we have seen the diagonal elements of Hermitian matrix are real. The same concept is applicable for eigenvalues also. The eigenvalues of Hermitian matrix are real. The eigenvalues of Hermitian matrix are real. Similarly, we have seen the principal diagonal elements of skew Hermitian matrix are purely imaginary or zero. In the similar manner, the eigenvalues of skew Hermitian matrix are purely imaginary or zero. Okay. Similarly, now the unitary matrix. Now we have seen the determinant of absolute value of the determinant of unitary matrix is unit modulus. That means plus or minus 1. So that in the similar manner, eigenvalues of unitary matrix are has absolute value 1. Eigenvalues of unitary matrix are of unit modulus also we can say. So these are the properties of complex matrices. Okay. Next, see problems on complex matrices. We see one problem first, which is show that every square matrix is uniquely expressible as the sum of Hermitian and a skew Hermitian matrix. That means consider a square matrix, okay, that can be expressed as sum of two matrices. One is Hermitian matrix, the another one is skew Hermitian matrix. We have to prove this one, and this is only a unique way possible. That means there is no other way. That we uniquely we have to we can express a square matrix as sum of Hermitian and skew Hermitian matrices. So now let's prove this one. See, to show that every square matrix uniquely expressed as sum of Hermitian and skew Hermitian matrix, first let us consider let capital A be a square matrix. Let capital A be a square matrix. Let capital A be a square matrix. And we can write this A as, we write this matrix A as, see A plus A theta. I am writing C here. Observe carefully. A can be written as A plus A theta. Okay. Plus A minus A theta. So observe here carefully what is happening. A plus A theta plus A minus A theta I am writing. So here plus A theta minus A theta gets cancelled. We are getting 2A, but which is actually A only. Let's do one thing, make it half. It is 1 by 2. And here also the same, it is 1 by 2. Okay. Now observe here. Half A plus half A, which is A, plus half A theta minus half A theta gets cancelled. That means a matrix A can be written like this, which is let us consider say P plus Q. Say, for our convenience, I am denoting this with P, this with Q. That is where P is equals to half A plus A theta, and Q is equals to half A minus A theta, That is A here expressed as sum of two matrices P and Q. That means if we can able to show P is Hermitian and Q is skew Hermitian, nothing but A is expressed as Hermitian and skew Hermitian matrices. How to show this P is Hermitian and Q is skew Hermitian matrix? Let's see. So to show that P is Hermitian matrix, we have to consider P theta. Consider left hand side. If A is any matrix, say, to show that it is Hermitian, we have to show that A theta equals to A. Similarly, to show that P is Hermitian, we have to consider P theta. Let us consider here. Consider P theta. That is 1 by 2 A plus A theta whole theta. Okay. Now, So now using the properties of complex matrices, anyway, this is 1 by 2, which is the real number, the conjugate of the matrix. This is observed here, it is in the form of k into a theta, k into some a, k into a whole power theta. K into a whole power theta is k bar into a theta, but k bar is k itself, since it is a real number, it is not complex. So the conjugate of complex number itself. And now power theta, a plus a theta whole theta. Okay, now this is equals to, it is now 1 by 2. Observe, this is in the form a plus b power theta. A plus b power theta is, as we know, that a theta plus b theta. A theta plus b theta. What is b? B is a theta. A theta power theta. Okay. Now, so since here we used the property, it is k into a power theta is equals to k bar into a theta. We used the property here, this one. Since k is 1 by 2, a is let us assume a plus a theta is a something. So k into a power theta is k bar into a theta. A theta we considered. K bar means, since it is 1 by 2 is a real number, its conjugate is itself. Okay. Now here we used the property. Here we use the property a plus b theta equals to, a plus b theta is equals to a theta plus b theta. Here we use the property a theta plus b theta. Next, it is 1 by 2. Now it is a theta plus, as we know that the property of complex numbers, a theta power theta is a itself. It is itself. That means, since, as we know the property is a theta power theta is equals to a only. It is a only. So now, observe here, what is 1 by 2 into a plus a theta? A theta plus a is same as a plus a theta, which is looks like same p as no. 1 by 2 a theta plus a, which is nothing but p only. Which is nothing but p only. That means p theta equals to p. P theta equals to p. That means p theta equals to p means, therefore p is Hermitian matrix. P is Hermitian matrix. Similarly, to show that Q is Q Hermitian, let us consider Q power theta. Okay, consider here Q theta. Q theta, what is Q? Same, 1 by 2 into a minus a theta power theta. Using again the properties of the complex matrices, first this is equals to, it is k into a power theta, which is k into a theta. Okay, used the same property here. I'm not writing again. Okay, the same property, k a power theta equals to k bar into a theta. Next, I am using the same property like this, a plus b power minus theta equals to power theta equal a theta plus or minus b theta. The same property here, it is a theta minus a theta power theta. Okay, now this is equals to again 1 by 2 into, this is a theta minus, as we know that again, it is, as we know that again, this is a theta power theta is a itself. We know again using this property. Okay, that is equals to, now let's take minus common from this, that is minus 1 by 2 into a minus a theta. If you take minus common, we get this. Observe carefully this half a minus a theta, half a minus a theta is q. Therefore, we can write it as minus q. What is this? Q theta equals to minus q. So q theta equals to minus q means we can say that q is skew Hermitian matrix. Skew Hermitian matrix. Skew Hermitian matrix. So that, see, A equals to, we write as P plus Q. We showed that P is Hermitian, Q is Q Hermitian matrix. That is, from this we can say any square matrix is equals to sum of Hermitian matrix plus skew Hermitian matrix. From this we can say any square matrix can be expressed as sum of Hermitian and skew Hermitian matrices. But this is one way. We have to show that this is the unique way that we can express the sum of Hermitian and skew Hermitian matrices. This is the only way we can express the matrix as sum of Hermitian and skew Hermitian matrices. So now generally what we do to prove that such kind of thing is unique, we have to assume that there exists another such kind of thing, okay, and finally we have to show that both are same. Both are same. So now to prove the uniqueness of this, let us consider that there exists another way of representing the square matrix as sum of Hermitian and skew Hermitian matrices. Okay, let's see. We consider here, to prove uniqueness. To prove uniqueness. To prove uniqueness, let us consider that there exists another way of representing a square matrix A as sum of Hermitian plus skew Hermitian matrices. So R and S. So here what I am saying, R is Hermitian, S is skew Hermitian matrix. R is Hermitian and S is skew Hermitian matrix. That is, A can also be. So previous slide what we showed, A is expressed as sum of P plus Q. P is Hermitian, Q is skew Hermitian. I am taking that A can also be expressed as sum of Hermitian and skew Hermitian matrices in another way. That is, R and S are two other different matrices, not like P and Q. I am considering like that. So R and S are two other, where R is Hermitian, R is Hermitian and S is skew Hermitian matrix. S is skew Hermitian matrix. S is skew Hermitian matrix. What is the meaning of Hermitian? Therefore, R theta equals to R. This already we know. Since R is Hermitian means R theta equals to R. And also S is skew Hermitian means S theta equals to minus S. S theta equals to minus S. Let us consider that we have A, no? Let's determine what is A theta. What is A theta? As we know that A is R plus S. So R plus S power theta, which is equals to, which is in the form of A plus B power theta. A plus B theta is A theta plus B theta. A theta plus B theta. Observe here, which is equals to, what is R theta? As we know that R is Hermitian matrix, R theta equals to R. Of course, S theta equals to minus S. Since S is skew Hermitian matrix, so it is minus S. So A theta equals to R minus S. A theta equals to R minus S. Okay. Now let us consider that A plus A theta. Consider A plus A theta. What is A plus A theta? See here. A equals to R plus S. What is A theta? R minus S. Okay, A plus A theta. A is R plus S. A theta is R minus S I am considering. So that these two gets cancelled, which is equals to 2R. Let's make it half. That is half A plus A theta, which is equals to half 2R, which is equals to R. Which is equals to R. Observe here, what is actually half A plus A theta? What is actually half A plus A theta? We know that half A plus A theta is P. Half A plus A theta is P. So that means R is nothing but P only. Nothing but P only. Similarly, consider A minus A theta. A minus A theta. That is A is R plus S minus A theta is R minus S. That is equals to R plus S minus R, minus into minus plus S. So plus R minus R gets cancelled, which is 2S. Now if you make it half, that is half A minus A theta, which is equals to half 2S, which is equals to S. What is actually half A minus A theta? We know that half A minus A theta is Q. Therefore, S equals to Q. That means we considered actually A can be expressed as sum of Hermitian and skew Hermitian matrix in a different way as sum of R plus S. But finally we proved that R and S are same as P and Q. That means there does not exist any such representation of expressing A as R plus S, which is unique, where R is P and S is Q only. Therefore, this is unique. So, therefore, we say square matrix equals to sum of Hermitian matrix and skew Hermitian matrix is unique. That means we can express any square matrix as sum of Hermitian and skew Hermitian matrices in one and only one way. There does not exist another such representation. Okay, uniquely we can express any square matrix as sum of Hermitian and skew Hermitian matrices. Okay, let's see one more problem. Okay, see a problem. What is given is A is a complex matrix given which is square of order 3 by 3. Okay, we have to show that A is Hermitian matrix and I into A is skew Hermitian matrix. I into A skew Hermitian matrix. First, let's show A is Hermitian first. A is Hermitian. A is no. To show that A is Hermitian, we have to show that A theta equals to A. A theta equals to A. First determine A theta means transposed conjugate of A. Transposed conjugate of A. So first we determine the conjugate. Next we determine the transpose of the matrix. So first conjugate of the matrix. A conjugate, which is, it is 5, which is real number. So 2 plus I conjugate is 2 minus I. Minus 3I conjugate is plus 3I. 2 minus I conjugate is 2 plus I. And minus 3 conjugate is minus 3. 1 plus I conjugate is 1. 1 minus I conjugate is 1 plus I. And plus 3I conjugate minus 3I. 1 minus I and 0. This is A bar. This is A bar. Next, A bar transpose. This is called transposed conjugate of A, which is nothing but A theta. Which is nothing but A theta. That is interchange rows and columns. So let's write first column as the first row. That is 5. It is 2 plus I minus 3I. First column as the first row. Second column as the second row. 2 minus I minus 3 and 1 minus I. Second column as the second row. Third column as the third row. 3I, 1 plus I, 0. Now let's verify with A. So first row is 5, 2 plus I minus 3I. 5, 2 plus I minus 3I. Second row 2 minus I minus 3, 1 minus I. 2 minus I minus 3, 1 minus I. Third row 3I, 1 plus I, 0. 3I, 1 plus I, 0. That means which is equals to the matrix A itself. The matrix A itself. That is A theta is equals to A. A theta equals to A. That means A is Hermitian is proved. A is Hermitian is proved. So therefore A is a Hermitian matrix. A is a Hermitian matrix. Okay. Next we have to prove I into A is a skew Hermitian matrix. So now let's see. We have A here. This is the matrix A. I into A. First we have to multiply this matrix with I. Scalar multiplication of a matrix with a complex number. I into A. We have to multiply every element of the matrix with the I. That is 5 into I. Okay. 2 plus I. 2 plus I. If you multiply it with I, what we get? It is 2I plus I square. I square means minus 1. I square means minus 1. Next, minus 3I. Multiplying it with I means I into I is I square. I square is minus 1. Minus into minus plus. So it is plus 3. It is plus 3. Next 2 minus I. 2 minus I means it is 2I minus I into I is I square. I square is minus 1 means minus into minus plus 1. Next minus 3 into I minus 3I. Here 1 minus I into I. So it is I minus I into I is I square is minus 1, minus into minus is plus, so plus 1. It is 3I square ante minus 3. 1 plus I, which is nothing but I plus I square is minus 1, and 0 into I, anyway it is 0. So this is the matrix I into A. This is the matrix I into A. What we have to prove is I into A is skew Hermitian. I into A, this is skew Hermitian we have to prove. So in order to prove that I into A is skew Hermitian, we have to prove that IA whole power theta is equals to minus IA. Minus IA. We have to show IA theta is equals to minus IA. This we have to show in order to show that I into A is skew Hermitian matrix. Skew Hermitian matrix. So first determine IA power theta. IA theta means first we have to find the conjugate. Later we have to find the transpose conjugate of A. First I into A conjugate. I into A conjugate. That is conjugate of this matrix. 5I conjugate is minus 5I. It is minus 2I minus 1 plus 3. It is minus 2I plus 1, and it is plus 3I. It is minus I plus 1. It is minus 3. It is minus I minus 1, 0. It is 0. Now the transposed conjugate of this. What is that transposed conjugate? IA power theta. Nothing but IA transposed conjugate of IA, which is nothing but. Now we have conjugate of IA. Now make it transpose. Interchange rows and columns. That is first column as first row. That is minus 5I minus 2I plus 1 and minus 3. Second column as second row. Minus 2I minus 1, 3I minus I minus 1. Third column as third row, 3 minus I plus 1 and 0. This is IA power theta. IA theta. Now what is, we have to show this one now. Left hand side we obtained. Let's see the right hand side. What is IA we have? Let's multiplying it with minus I. Minus I into A. Minus I into A. We have I into A. Multiplying it with minus. Multiplying every element with minus sign. That is minus 5I. Now this becomes plus minus 2I plus 1. Multiplying with minus 3. And it is minus 2I minus 1 plus 3I and minus I minus 1. It is plus 3. It is minus I plus 1. Of course it is 0. Now you can look at these two matrices. Observe the first row, minus 5I, minus 2I plus 1, minus 2I plus 1, minus 3, minus 3. Similarly, the second and third rows are same. That means IA theta is equals to minus IA. So hence IA power theta is equals to minus into IA. Okay. So therefore IA is a skew Hermitian matrix. Skew Hermitian matrix. Okay. So like this, a matrix A here given is showed as Hermitian matrix, and I into A is showed as skew Hermitian matrix. Okay. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.